much, Prathamesh. Visible and can be heard as well. Gallium nitride has featured prominently in a great many of the talks in this World Microwave Congress. And of course, it's both in this session and other sessions. And it's responsible for a great many advances recently in the world of microwaves. Gallium nitride is the centerpiece of this talk as well. I'd like to focus on the distinct characteristics of these gallium nitride FETs themselves. So I guess we're all aware of the fact that gallium nitride provides very high breakdown voltage, very high full channel current and full channel charge. And in fact, the channel charge density is higher than the donor doping that's put into the device itself. This is pretty well known. Actually, this particular figure is something I began a talk with in 1998. So with us for a long time. Of course, gallium nitride is endowed with a host of wonderful characteristics, particularly for power amplifier applications. Breakdown electric field at 3.3 megavolts per centimeter is about 10 times that of silicon. Has a channel mobility of 1,000 centimeters squared per volt second in the 2D electron gas form, which is 5 times higher than silicon and on a par with other 3.5 devices. Electron velocity is very high, can exceed 2 times 10 to the 7th centimeters per second, and extends over a very wide range electric field. And the thermal conductivity, particularly on a silicon carbide substrate, is really spectacular. So these things are well known to almost all of us. And without any doubt, one could say that in the area of power amplifiers for heavy lifting, we should use gallium nitride. Now, there's a question of how to best utilize the nitride FETs, however. Should we just use traditional design to the concept and turn up the current by 1 notch, perhaps by 2 notches? The answer is probably no. Gallium nitride has some unique characteristics that dictate, to some extent, the concepts we should use, the circuit approaches that we should use. I'd like to describe those within this presentation and go through a list of differences one by one. And these differences stem mostly from the materials properties and basic physics, but they do translate into information about how to make the FETs and how to use them. So to begin with, I should mention that as we probably all have heard, that the carrier densities within the gallium nitride FETs stem largely from differences in polarization between the channel and the overlying material, typically aluminum gallium nitride. Polarization stems from both the electric effect. In fact, gallium nitride has very high polarization electric coefficients, almost on a par with materials that are selected exclusively for their piezoelectricity. And there's also a spontaneous polarization like exists in ferroelectrics, except the nitrides, it's not switchable. So these polarization vectors are directed perpendicular to the wafer surface. They form a difference interface between the two materials. Polarization is part of the electric displacement field, the D field. And according to Maxwell's equations, when there's a difference between D fields, there's a charge density, and that provides the interface charge drives gallium nitride FETs. The situation is clearer if we look at the band diagram. I cut through the structure normal through the gate channel, and the results are shown here. At the interface, in barrier and channel, there's a significant positive polarization charge. And this is compensated by a 2D electron gas that forms at that. Interesting and important to notice also that there's a corresponding polarization charge that's negative that forms at the surface of the AlGaN, essentially equal to that earlier interface. This is compensated in turn by a positive charge associated with a depletion of the electrons in the metal over a very short distance. The polarization charges in 2D electron gas densities can be very high, typically on the order of 10 to 15 electrons per centimeter, which is higher by a factor of 2 or 3 than obtainable in other 3-5 FETs. And the polarization charge can actually be increased substantially by changing the material for the barrier. And here are some simulations showing what can be done with aluminum nitride, and a lot of exploration today about the use of scandium aluminum nitride, for which the overall 2D electron gas density can reach 2 or 3 times 10 to the 13 per centimeter. Of course, what you agree to, you could deposit these materials on the gallium nitride depends on the lattice mismatch, the different materials. I should note, however, that there's a practical limit to how much polarization charge you would wish to have for the 2D electron gas, because after all, in a FET, you have to turn that charge on and off by application and the gate. The electric field that is established to modulate the charge is limited both by breakdown electric field of the dielectric material that you use, and perhaps by Fowler-Nordheim tunneling. So, in fact, in the case of silicon, the limits on the charge density that you can obtain are also on the order of 10 to 13, or even a little bit higher. It is limited by the breakdown field dielectric constant, the SiO2 oxide that's rarely used. And for that matter, it's really the D vector rather than E vector. Right, so high K dielectrics that have high epsilon can possibly reach higher levels by charge density that modulate usefully within FETs. But there's another consequence of the polarization charge formation that bears discussion. So it's rather easy to see what goes on within the FETs immediately with the gate metal. In general, however, there's a relatively large distance separating the gate and the drain. And here, the picture is a little bit less clear. Once again, there's polarization charge positive at the interface between channel and barrier. And associated with that, there's the 2D electron gas. But on the surface of the AlGaN, there remains the negative charge. And this is compensated for the most part by a deficit of electrons in surface state. But it's really a surface that controls the charge balance within this region. The surface states themselves are things that are most nitrides, they're controlled by past history of the material, the preparation technique, and in fact, can be dependent on applied voltage. And the fact that the surface states are deep levels, and deep levels exist elsewhere in the material, is very important for the gallium nitride behavior. The deep levels have an important role. They exist in part as, well, gallium nitride has density of dislocations, lattice mismatch, typically on the order of 10 to the 8th square centimeter. But in addition to defects that are introduced via the dislocation, there are numerous point defects, the native defect. These occur because high growth temperature, the fact that wide bandgap material. Native defects can include vacancies, gallium or nitrogen, initials of gallium and nitrogen. And they form, actually, to some extent, it's energetically favorable for them to form. Being deep in the material, it's energetically favorable if electrons can reside in these deep levels instead of being in the conduction band, self-compensation. Now, one of the features of the point defects from states within the bandgap, they are traps, and the trap time constants can be long, considerably longer than those semiconductors. Particularly the emission time from traps is a thermally activated mechanism. The deeper the trap, the longer the time the traps to release their charge. So for a representative example, for a given capture cross-section and number of traps, you might have a capture time constant on the order of 5 nanoseconds of nitride materials. If the trap has a depth of 0.2 eV, then the corresponding emission rate can be calculated to be about 11 nanoseconds. This might occur in 3/5 or silicon. But if the trap depth is 0.5 eV, then this becomes 1.2 millisecond for a 1 eV trap. The calculated emission time is 80 hours. So the trap occupancy actually is a function of history, and you never can be quite sure you have with a given gallium nitride. Now, the traps have significant effects on the IV curves. Their occupancy changes and the IV curves. The effects that have been observed have various names that correspond perhaps to somewhat overlapping mechanisms that are known as drain lag or gate lag, dynamic on resistance, knee voltage wall collapse, and also hysteresis. A typical basic character corresponds to measuring DC IV curves on a static basis, then repeating those on a pulse basis, where both the drain voltage and the gate voltage are pulsed to the IV voltage characteristics for the measurement of the IV. But then the steady state or quiescent initial values, drain and gate voltage can be different. And the IV curves depend on those quiescent voltages. Finally, for example, starting drain voltage at 20 volts of 0, then you would get IV curve corresponding to the dotted line here. Because of the different occupancy traps is determined by the higher. So as the drain voltage is changed, then the IV curves here for a completion mode FET measured at a constant VGS of 0 volts, then those IV curves change and they correspond to lower current, higher on resistance, their value, quiescent drain voltage. Now, this is particularly troublesome in the world of power amplifiers. As you apply higher voltage, well, one would expect that higher VDD, the output power is obtained in a low measurement, but would increase linearly value. But experimentally, this is often the case. In fact, at a lower rate in a linear. These data, these charts are from more than 10 years ago, and they exaggerate the problem. But still is an effect that is present, less severe. Important for design, these effects can be taken into, they're somewhat useful. So in principle, you can design around them, saturated power at a given volt, but they're hard to model and know with precision. One of the mechanisms that's relatively easy, dominant mechanism, is that of hot carrier injection. This is something that's very well case of silicon MOSFETs. When there's a high drain voltage, electrons traveling from source to drain can pick up enough energy that they can scatter overlying the CO2 and trap there and create defects. So a similar effect occurs in nitride FETs. If you have 20 volts on the drain, then to expect the electrons traversing the gate to drain region will pick up enough energy so that they can scatter into the algan and trap there, or perhaps make it to the surface and be trapped, from which they then tend to compensate the charge in the channel, modulating its carrier density and leading to excess resistance. They stay there for a significant length of time due to the load from the. Overall, the electric field within the material between gate and drain is a very important parameter for the operation of the FET. One wishes to have a constant electric field gate and drain to maximize breakdown voltage. However, in most cases, there's a buildup of the electric field, particularly at the gate junction on the drain side. It leads to leakage and breakdown and trapping. This can be mitigated to a considerable extent by the use of field plates that are connected to the gate, or perhaps having a field plate connected to the source. These change the overall pattern of the electric in this region, as shown here for calculations with lengths, and they decrease the electric field at the edge of the gate and distribute it over a greater. So this is a very important characteristic of the FET. The field plates are good to extend the breakdown. They have a very important role in trading off capacitances, particularly the source field plate, you can understand, tends to field the gate itself, diminishing E, but increasing S. The extent to which they lengthen the depletion region, it decreases E. Another characteristic of the gallium nitride FETs that I'd like to turn to is the technology is more limited. And the fact that you do not have ion implantation and diffusion techniques standardly available means that the doping is primarily determined by crystal growth. And in the past, it's been associated with a single epitaxial growth of the entire device. The second epitaxial growth has been introduced, expands the possibility. If there's a single growth, a single polarization charge, then there isn't the opportunity to directly tailor what is going on within the gate to drain region to form, for example, the lightly doped drain region, which are part and parcel, or the EMOS. That's a limiting factor. Another issue is that in the source to drain source to gate region forms basically the series resistance of the course, the channel charge is typically slightly lower than the channel charge in the gate. And in fact, the current saturates. It can add some degree of current. So this is one of the factors that causes gallium nitride FETs to have a characteristic very rapid drop of GM as VGS. I should mention, and we'll be turning to later, that the major factor GM drop off different effect, scattering within the 2D masses. Another issue associated with processing of nitride FETs, it's a very fortunate one, that the nitrides are a bit more tolerant, resistant to formation of interface in ALD deposited dielectrics, and the nitride allows different electrics to be deposited in order to form MOS or MIS structure. This is favorable for making enhancement mode FET, such that when you forward bias the gate source junction, you don't get current flow at 1 or 2 volts, or conventional area. I should note that also a more recent development, and is particularly in the world of power electronics, is that it can form P-gallium nitride grown on top of it. Then you get a turn-on voltage for the associated PN junction very high because of the large band gap of the gallium nitride, and also the fact that you're sandwiching air of very wide band gap aluminum gallium nitride between the P and N region. I'd like to now discuss the fact that gallium nitride devices typically have not been scaled. Otherwise, we'd be talking today about 5 to 10 nanometer gate length, about 10 volt ground voltages, devices that could be used. So first, there's an important question: why would we like this? And the answer is perhaps twofold. One is that in order to address applications at a gigahertz or above, very necessary to increase FT and Fmax, and that it's also desirable to address applications, for example, smartphones, having efficient voltages, power supply voltages less than 10 volts. For this, we need to have knee voltages that are very low, half a volt. That's preferably very low on resistance. That, once again, requires increasing the overall effects, for example, on FT, be appreciated with this sort of toy model measuring the source and drain into dimension and things. But overall, the FT is dependent on the different distances and time of travel of electrons through that distance between source and gate, across the gate and drain. And we need to shrink these to get higher FT. And it's well established, however, that this means coordinated scaling of the vertical dimensions of the device. Well, otherwise there is a fringing field between the gate and the material. Scaled vertically, one wants to decrease the electric thickness, or if you will, in the world of Moore's law, and this increases the capacitance, density device. But it also increases the GM by the same amount, and this sort of out. So get an increase associated with the thinking of the device. get higher FT. This can be accomplished by nitride by using actually aluminum nitride layer for dioxide, silicon nitride in different configurations. For lateral scaling a device, this is something that's rather difficult to do if you want to, particularly if you have get the source and drain regions very the gate. It's been carried out successfully, well, initially and prominently in work at HRL. And the figures here show differences between be done with aggressive scaling, the grown source and drain contacts close versus an unscaled and allows much larger drain extension under application of the drain field. Have breakdown voltage, but so on this basis of the lateral scale.
Professor Peter,
yeah.
Sorry to interrupt you. Looks like there's some issue with your microphone. Could you please try closing off your camera? Maybe that will help with the bandwidth.
Sure. Let me see. Yeah, sorry about that. I don't perceive that from this side. So, okay. I don't know if speaking louder would make a difference. The breakup, I can't detect. In any event,
maybe you could come a little close to the microphone. That might help.
Yeah. Okay. So on this basis, the scaling has reached FTs of 450 gigahertz, which I believe is the record at the moment. Now I'm having so as let me see scaling the dimensions, it's kind of a two-edged sword. There's the benefit of increasing FT, but there are also issues associated with increasing the CGD and the coupling between the drain voltage and the channel itself. That's something that tends to increase GDS as well, and as GDS. So there are issues of increased output conductance as a result of that. Part of it is from the sort of self-backgating or Dibble effect. Another is associated with the fact that CGD itself increases the output conductance of the devices. So, for example, an application of a field to the drain increases the voltage at the input side, which through GM leads to a higher value of output current. So from both of these effects, the overall output conductance of the device is increased. The associated resistance is decreased. Also, the breakdown voltage decreases. As a result of these effects and others, there's an impact on the impedances that one would wish to use within the device. For a power amplifier application, we're in general guided by the DC IV curves in the choice of the load resistance that we wish to apply. In the case of gallium nitride, of course, the maximum voltage that can be obtained is much greater than for more conventional FETs. For the same dimensions, the current is about the same, and as a result, optimal load resistance is much higher than for other FETs. On the other hand, if we look at the output conductance that we were just discussing, it's on the same order as obtained for other FETs because of the increased gas and CGD, particularly in the case of noise. So the ratio of RL optimal to R out can be higher than for other FETs. And this can lead to a number of consequences. If we apply RL greater than R out, then that reduces gain and can lead to high S22. High RL also increases the effect of GGD on stability. The voltage gain that you obtain with the FETs tends to be higher than with other FETs. For example, for gallium nitride with an input swing of 6 volts and an output swing of 90 volts, Miller factor is about 15. By contrast, on the other extreme, for CMOS, you might have a 2-volt input swing and 3-volt output swing, leading to a Miller factor that's 10 times lower. So CGD can have a major influence on the capacitance of the device, and including nonlinearity effects, the injection of the output input side. So these are things that are recognized by gallium nitride FET designers. And so for low frequency applications, useful to suppress CGD by using a large distance between gate and source and field. These are good. So for example, if you look at devices of gallium nitride used for high voltage, 100 volts or above, in sub-6 gigahertz application, you find that the ratio between CGS and CGD is quite high, of order 50 or so. A gallium nitride device that is applied at higher frequencies tends to be designed with a lower ratio of CGS to CGD, and this might be in the range of 20 or so. In contrast, in gallium arsenide and PHEMS, an associated ratio CGS to CGD might be 6. And in CMOS SOI with the symmetric digital-like structures, the ratio is 1. So these are good designs for low frequency, but they come at a cost in FT. There's still output capacitance, but it's now dominated by CDS rather than CGS. But it's true more generally that RL can be much higher for FETs of gallium nitride, but the output capacitance is relatively the same for FETs of the same dimensions as other FETs. This means that the load impedance has higher Q ratio between the reactance and the resistance. In this case, I'm talking about a parallel combination of the resistance and the reactance. This is something that at low frequency, it does not matter, but at high frequency, it does. As an example of implications, I show here some notional designs for a frequency of, in this case, 75 gigahertz, for a notional gallium nitride device and a corresponding CMOS device. Now, the ratio between voltages applied is immense, and the output powers is also, well, really different for the two cases. But if we look at the loads for gallium nitride, the effective load resistance is 130 ohms because of the very large ratio between the current. And that's 10 times higher than the value chosen for the CMOS. But the capacitance associated with this is almost on the same order, so that the Q for the gallium nitride device high, it's 5 at that high frequency. And for the CMOS, it's less than 1. So it's not really an issue. The high Q load is important. It reduces the bandwidth achievable, requires very good passives to obtain high efficiency. And it can limit the effectiveness of load modulations. For example, in a Doherty, if you change the real part, the load impedance, well, that get swamped by the very high reactance. But in response to the need for high Q passives, gallium nitride FET technologies provide this with low loss substrates, air bridges, lots of area. Okay, a couple more things to mention. Models tend to be incomplete for the gallium nitride. Typical models have parameters that are adjusted for the case of gallium nitride to more or less correspond to the capacitances and conductances, but they've typically not covered adequately are the trap effects, particularly the impact of VDE and VDS, the on resistance, and the knee voltage walkout. And this is quite important if you wish to design power amplifiers, because it corresponds to the scaling of output power with the drain voltage. Another issue is that it is difficult in standard fashion, standard equations to express properly the nonlinearity of GM and capacitance. Some thermal effects. Issues associated with these effects can be described with substrate. So, for example, to describe the trapping effects, one wishes to have subcircuits that measure and account for the amounts of charge in the different traps. Then have accordingly changes in threshold voltage and on current and drain resistance that are trap dependent. This is a manner similar to what it's done for the self-heating with the subcircuit, taking account the time-dependent self-heating primary effect. Now, in recent years, there have been significant improvements in the models that are available, nitride FETs, and a couple of them are shown here. For example, there's the GaN FET model from Keysight, which there are the subcircuits to indicate the trapping, and these properly account for the difference between the capture current and the emission current or upward leads current for both the gate and drain sources, as well as self-heating. Now, the overall IV curves are constructed by a neural network trained by lots of data. Another very powerful model is ASM-HEMT model from IIT Kanpur and University of South Florida. In this case, there is an analytic formalism with the IDVDS and circuits for trapping and self-heating. And this is capable of accounting very well for the voltage-dependent on resistance and voltage walkout, as well as fitting under various bias conditions, the output power and efficiency of trapping effect. Now, as a final note, I'd like to fact that the technology for gallium nitride is continually under development, and to some extent, the effects I've discussed are changing and being mitigated year by year. One highlight is the lateral scaling that has emerged in what I've talked about in the work at HRL, with both the vertical and lateral scaling, with the use of aluminum nitride, very thin dielectrics, 3.5 nanometers. Another very important development is the emergence of hydrogen polar gallium nitride, in which case the substrate is flipped upside down, so the 2D electron gas forms on the top surface of aluminum gallium nitride of it. And this places that 2D electron gas closer to the surface where it's easy to make very good ohmic contact and to scale device length. This is work that has been done in Umesh Mishra's lab at UC Santa Barbara, in addition to all the other work on the development of nitrogen that he has done, and the work for electronics. It's now emerging as something that is getting a lot of attention in areas around the world. Another issue is associated with bridge FETs and FinFETs. And in this case, the channel charge is modulated by fields that are applied laterally from the gates in addition to the vertical case. This allows, among other things, to have very low source resistance, because the source region covers a much wider area than the region within the channels under the gates themselves. Also, it allows multiple channels to be built up within the material in order to have much higher output. There is incredibly impressive work emerging from Intel in work of Conway and his colleagues, with the growth of gallium nitride on 300 millimeters silicon wafers, with a truly well-developed scaled process, including the overgrowth of contacts, the use of lattice-matched indium aluminum nitride, and very short gate lengths. The device performance, wonderful, very uniform across the large wafers, and your increasing series of demonstrations, very high performance. As a final note, I'd like to discuss the graded channel gallium nitride work that has been emerging, and it's associated with the fact that the aluminum gallium nitride is graded for 10% range over a distance of 6 nanometers, instead of having the usual abrupt junction in the barrier and the channel. And in this case, the polarization charge leads to essentially a 3D electron gas instead of the usual 2D electron gas. And this succeeds in increasing the electron velocity, which tends to saturate very high current barrier densities for the case of the 2D electron gas. It allows the voltage, the velocity to be increased within the devices. And this leads to IFT. It suppresses the very large drop-off of GM that occurs in devices between saturation of the velocity. Thus, improves the GM versus voltage. And it decreases the so that trapping effects the T-gate temps. With that, I'd like to end with a quick outlook. Gallium nitride and related nitrides have lots of material advantages for electronics, but they also have a lot of idiosyncrasies. Continue to be new opportunities for understanding and harnessing their unique properties. So as a result, the nitride area continues to be a worthwhile and enjoyable area for research. And so thanks for your attention. I'd like to open things for questions.
Thank you so much,